Assalamualaikum and good day. So today our group will present about Faraday's law in action, wireless energy transfer and distance dependency in coils. These are all our group members. Now let's move to objective of this experiment. There are three main objectives from the experiment. First one is to investigate the effect of distance between coils on the efficiency of energy transfer. Second is to observe the practical application of Faraday's law in wireless systems. And finally is to explore the concept of wireless power transfer through inductive coupling between two coils using an alternating magnetic field.
There are three theories that we apply throughout in this experiment. The first one is Faraday's law of electromagnetic induction. This theory applied when an alternating current flows through the first coil, which is transmitter. It creates a time-varying magnetic field. If a second coil, which is receiver, is placed within this changing magnetic field, a voltage electromagnetic field is induced across it. This theory comes out with an expression which is induced voltage is equal to negative number of turns in the coil times with rate of change of flux. The second theory that we apply in this experiment is mutual inductance. Energy is transferred wirelessly from coil 1 to coil 2 through inductive coupling, where the magnetic field from one coil induces current in another. The efficiency depends on the distance between coils, coil alignment, and operating frequencies. And the third theory that we apply in this experiment is near field transfer. This method of energy transfer is considered near field, meaning it uses the magnetic component of the electromagnetic wave, not related far field electromagnetic wave like radio.
To start the experiment, we need all these components, which is a sandpaper breadboard, coil, ruler multimeter, function generator, and lastly LED. So for the first step, wrap the wire around a circular item like a bottle or tube to create two coils, each with 30 turns shaped evenly and neatly. Second step, gently sand the end of the coil wire using sandpaper to remove the insulation and expose the copper. Third step, construct the circuit as shown, ensuring the first coil is connected to the function generator and the LED is connected to the second coil. For the fourth step, set up the function generator as shown, adjust the frequency to 150 kHz and set the output voltage to 10 volt peak to peak and then turn on. For the fifth step, make sure the multimeter is set to AC mode voltage, then measure the voltage across the LED and observe the reading. And lastly, increase the distance between the two coils and repeat the step 5 to observe how the induced voltage change. As the distance increases, the LED brightness decreases. Conversely, the closer the coils are, the brighter the LED becomes. As for the result, this graph shows the relationship between the distance of the coils and the AC voltage induced in the receiver coil. When the coils are placed close together at 2 cm, the induced voltage is about 2 volts, the highest point, which is indicates the strong magnetic coupling. As the distance increases to 4 cm and then 6 cm, the induced voltage drops significantly to around 0.8 volts and 0.4 volts. This shows that increasing the gap between coils weakens the magnetic field interaction, resulting in less energy transfer to the receiver. This observation is consistent with Faraday's law, which states that a changing magnetic field induces a voltage in a nearby coil, but the strength of this induction depends on the proximity and alignment of the coils. So we can conclude that wireless energy transfer using inductive coupling is most effective at short distance where the magnetic field is stronger and flux linkage is higher.
Faraday's law shows how a changing magnetic field induces an electric current in a nearby coil, forming the basis of wireless energy transfer. In this process, a primary coil generates a magnetic field that transfers energy to a secondary coil without physical contact. However, the efficiency of this transfer strongly depends on the distance between the coils. As the distance increases, the magnetic field strength and the flux linkage decrease, leading to a significant reduction in induced voltage and power transfer. This wireless energy transfer is most efficient at short distance where magnetic coupling is strongest.
These experiments demonstrated wireless energy transfer between two coils using electromagnetic induction. When the transmitter coil was powered with an AC signal, it generated a changing magnetic field that induced voltage in the nearby receiver coil, lighting up an LED. As the distance between the coils increased, the LED brightness decreased, showing weaker magnetic coupling. This supports Faraday's law, which states that a changing magnetic field through a coil induces an electromotive force. The results highlights how coil distance directly affects induction efficiency.